How are you, learner? Welcome to Manifesting e-learning platform. My name is Purity Anzelimo, taking you through physics. And our lesson today, we continue with the topic in book 3, in paper 1, that is quantity of heat. So that's still our topic, quantity of heat. In our previous lesson, we were able to explain the topic, the meaning of quantity, what is heat, and we were also in a position to define heat capacity. So before we look at our subtopic for this lesson, we can do a recap on what we covered during the previous lesson. That was the introduction bit of quantity of heat. So we looked at heat capacity, and we said that heat capacity is denoted using which letter? Capital letter C. So that is heat capacity. So what did we say is heat capacity? So when we talk of heat capacity, we defined it as the amount of heat required to raise the temperature of a given mass of a substance by 1 Kelvin. So we can define it here and say that this is the amount of heat. So that is heat capacity, the amount of heat required to raise the temperature of a given mass of a substance by 1 Kelvin. And therefore we say that heat capacity, C therefore, will be equal to the heat absorbed, or maybe the heat given out, which is denoted by Q, divided by the change in temperature. So heat capacity is equal to heat energy divided by change in temperature. And from this we were able to get the SI unit of heat capacity, which we said the SI unit of heat capacity is joules per Kelvin. So the SI unit is joules per Kelvin. So we are going to do one question on heat capacity, then we can move on to our next subtopic. So we look at this question and work it out together on heat capacity. So that's the question that we have. So we have an electric heater rated 300 watts, heats some liquid of heat capacity 1680 joules per Kelvin in 2 minutes. So we are going to find the rise in temperature. So in our question, we are being asked about the rise. So this is simply the change. And in our case here, it's a rise. So we want to get that change in temperature. So we have been given the power rating. So we have been given the power as 300 watts. Again, we have been given that it is being used, that heater is being used to heat a liquid of heat capacity. So we have the heat capacity as 1680 joules per Kelvin. And the time taken to heat, the time is 2 minutes. We have 2 minutes. So we are going to find the rise in temperature. So we want to get the change in temperature. That is what is in question, because a rise is now the change. So for example, if it was 30 degrees Celsius and then it rose to 70 degrees Celsius, the rise will be 70 minus 30, which is 40. So we want to get that change in temperature. So in this question, we need to remember what we have said about the heat capacity. We have said that heat capacity will be given by the quantity of heat, or the amount of heat, divided by the change in temperature. Now, in this question, we have been given the heat capacity. It's here in its SI unit. But now we need to calculate the amount of heat, Q. So we need to calculate Q. And in this case, it is now we are using an electrical method because we are using an electric heater which is rated 300 watts, and it is heating the liquid for 2 minutes. And we know that heat energy will therefore, from the topic heating effect of an electric current, heat energy will be given by power multiplied by time. Power multiplied by time. And this one can be gotten from the Joule's law, whereby we say that the heat energy is equal to the current squared multiplied by the resistance multiplied by time, which we call the Joule's law. So from this, we can be able to get that from Ohm's law, since we know from Ohm's law V is equal to IR, we can substitute where we have R from this, we can therefore say that therefore R will be equal to V all over I, meaning that in this equation Q, we are going to have I squared multiplied by R, which is V all over I multiplied by time. So here one current I will cancel with 1, we remain with 1. So we end up getting our heat energy to be IVT. But we know that IV is equal to power. This is power. And therefore heat energy, the quantity of heat can be given by power times time. So we can go back to our question. So we have Q, we can be able to get the heat energy, which is power times time. And power we are given in its SI unit, which is 300 watts. Watt is the SI unit of power. We multiply by time. We are given time in minutes. And we need to express it in its SI unit, which is seconds. So we must convert the 2 minutes into seconds by multiplying by 60. So what do you end up getting? So we end up getting, this is 3 times 2, which is 6. 6 times 6, we get 36. So we have 36,000 joules. That is our heat energy. So we continue. Remember, we still want to get the change in temperature. So our heat capacity is given as, from this is 1680 joules per Kelvin is equal to our Q, which is 36,000 joules divided by the change in temperature. So we still want to get that change in temperature. So we have that 1680 joules per Kelvin is equal to 36,000 joules all over the change in temperature. So we can cross multiply so that we can get the value of the rise in temperature. So we are going to have 1680 joules per Kelvin, then multiplied by the change in temperature is equal to 36,000 joules. So that is what we have. We want to remain with change in temperature, so we can come and divide both signs by 1680 joules per Kelvin. 1680 joules per Kelvin. So we are going to cancel that by 1680 joules per Kelvin, 1, 1. So we remain with our change in temperature as, here we are having joules and joules per Kelvin. So this one will end up being, for that part, so that we can see the unit, it's like we are having joules, we are dividing by joules per Kelvin, that way, which is the same as joules multiplied by Kelvin per joules when we reciprocate, so we can cancel. So our answer will be in Kelvin. So you can take your calculator and divide 36,000 divided by 1680 to 1 decimal place. What is the change in temperature? You end up getting 21.4 Kelvin. So that will be our change in temperature. That is the change in temperature, or what we are calling the temperature rise. Hopes you got the question. So you can be given a question. It must not be. It can also be one testing on the electrical method of heating, whereby now we'll be talking of the power rating and therefore heat energy being given by power times time. And I have explained this from Joule's law, from the heating effect of an electric current. So that is it on heat capacity, the amount of heat energy required to raise the temperature of a given mass of a substance by 1 Kelvin. So in our lesson today, we look at something different in this lesson now. So we've looked at heat capacity, and now we want to move ahead and look at specific heat capacity. Specific heat capacity. Specific heat capacity is denoted using a small letter C. So you must be very keen, because the difference between a small letter C and a capital letter C is only the size. So you can see in my case here for the heat capacity, I'm using a capital letter C, but for specific heat capacity, we use a small letter c. So that is specific heat capacity. And in our lesson today, you will be able to define heat capacity. We'll know what is heat capacity, and also you'll be in a position to get involved in numerical calculations involving the specific heat capacity. So by the end of the lesson, you should be in a position to define specific heat capacity, and you should also be in a position to calculate or to involve yourself in calculations involving the same. So we start with the definition of specific heat capacity. Now when we talk of specific heat capacity, it refers to the amount of heat energy required to raise the temperature of a unit mass of a substance by 1 Kelvin. Now make the difference between the heat capacity and the specific heat capacity. We can first have that definition here. So we are saying that it refers to the amount. Now look at this definition. We are saying specific heat capacity is the amount of heat required to raise the temperature of a unit mass of a substance by 1 Kelvin. Now if you look at this definition and you look at the definition for heat capacity, what is the difference? This is where the difference is. For heat capacity, we are talking of a given mass of a substance. But in specific heat capacity, we are talking of a unit mass of a substance. So make note of that. The only difference between the heat capacity and specific heat capacity is that in the specific heat capacity, we are talking of a unit mass. So here we'll consider the mass of the substance. And therefore, from this, we can say that specific heat capacity denoted by a small letter c will be equal to heat energy or heat absorbed denoted by Q divided by mass of the substance, because here we are talking of a unit mass of a substance, mass multiplied by change in temperature. We can first write it mass, the symbol for mass is small letter m, then multiplied by temperature change. Temperature change denoted by this change in temperature. So we can therefore say that the specific heat capacity will be given by heat energy Q divided by mass multiplied by change in temperature. And that is our formula for calculating specific heat capacity. So it's equal to heat energy or heat absorbed divided by mass multiplied by the change in temperature. And therefore, from this, we can be able to get the SI unit of the specific heat capacity. We know that from this, we are saying that our specific heat capacity is equal to heat energy divided by mass multiplied by the change in temperature. We know the units for heat energy, joules. The unit for mass, what is the SI unit of mass? Kilogram. So we have here kilogram. And what is the SI unit now for our temperature? Kelvin. So we have Kelvin. And in this, it simply means we are dividing heat energy by mass. Then we divide it by the change in temperature. And therefore, the SI unit of specific heat capacity is joules per kilogram per Kelvin. So we can note that one down, that the SI unit of the specific heat capacity is joules per kilogram per Kelvin. So the SI unit of the specific heat capacity is joules per kilogram per Kelvin, which is written as joules per kilogram per Kelvin, or can be written as this, joules per kilogram per Kelvin. So we can have it either this way or that way. So that is the SI unit of the specific heat capacity. Now, we can also give it another different approach. We are saying that specific heat capacity is given by heat energy divided by mass multiplied by change in temperature. But now we know very well that, heat energy divided by change in temperature is equal to, what did we say? Heat energy divided by change in temperature is equal to heat capacity. Capital letter C is equal to heat capacity. And therefore, it means that our specific heat capacity, small letter c, will therefore be equal to this Q divided by change in temperature. All of this is heat capacity. So simply all of this is heat capacity, so is equal to heat capacity denoted by capital letter C divided by mass, M. And therefore we can also say that specific heat capacity is given by heat capacity divided by mass. And that is another formula that we can use to calculate specific heat capacity when we have been given the heat capacity. So we can also say that specific heat capacity is heat capacity per unit mass. So that is it, and those are the two formulas that we are going to apply in calculation of the specific heat capacity or any other quantity related to the same. So hope you've gotten those definitions for specific heat capacity. We have seen that it is the amount of heat required to raise the temperature of a unit mass of a substance by 1 Kelvin. So the key ones here are amount of heat. Then we are saying that a unit mass, raising the temperature of a unit mass of a substance, then by 1 Kelvin. And then we have also defined specific heat capacity as heat capacity per unit mass. And it is clear from here, since we've seen that the SI unit for heat capacity is joules per Kelvin, and we know that the SI unit of mass is kilogram. So we are dividing, and therefore the SI unit of specific heat capacity from this formula is still joules. We start now with our kilogram per Kelvin. So it is still joules per kilogram per Kelvin, which is the same here because we have joules per Kelvin per kilogram. So joules per kilogram per Kelvin, that's how we arrange it. So that is on specific heat capacity. So I want us to look at various examples and see how we can calculate the quantities that may be asked in such a question. So we look at examples. So I'd like us to go through that question together. A block of copper of mass 10 kilograms and specific heat capacity 460 joules per kilogram per Kelvin cools from 80 degrees Celsius to 40 degrees Celsius. Find the quantity of heat given out. So we are calculating the quantity of heat. Our Q, it can be heat absorbed or it can even be heat that will be given out. So in this case, heat is being given out. So we start by analyzing the question. We have a copper of mass 10 kilograms, and we can see mass is already in its SI unit. Then we have the specific heat capacity of 460 joules per kilogram per Kelvin. It is cooling from, so the initial temperature is 80 degrees Celsius and the final temperature is 40 degrees Celsius. So from this we can get the change in temperature. For us to get the change, we simply subtract. If we take 40 minus 80, we'll get negative 40. That negative simply means that it is a fall in temperature. So we don't need to consider that negative. It only means that it is a fall. So when you are getting the change, you can simply take the bigger temperature, the larger one, which is 80 minus 40, and you end up getting 40. This 40 can either be, we can talk of it being in Kelvin, because in our previous lesson, I explained why we don't have to change this temperature in Kelvin, because even if we change it in Kelvin, the change will still be the same. So we have the change in temperature as 40, so we can move ahead, and now we are asked in this question to calculate the quantity of heat given out. So we'll come and apply our formula on specific heat capacity. So we've seen that specific heat capacity is given by the quantity of heat divided by mass multiplied by change in temperature. So our specific heat capacity, C, is 460. So it's equal to the quantity of heat, which is now in question, divided by mass. The mass is 10 kilograms, and the change in temperature is 40. So we have, therefore, 460 is equal to the quantity of heat divided by 400. So to get Q, we just come and cross multiply. So our heat capacity will be 460 multiplied by 400. So therefore, you just use your calculator. We have 460 multiplied by 400, and you end up getting 184,000. And this is heat energy, and since all the other units are in the SI units, we get the heat energy in joules. So that is the quantity of heat that is given out. This is a large number. We can change it into kilojoules. We know that 1,000 joules make a kilojoule. So by dividing by 1,000, we can still say it is 184 kilojoules. So that is the heat energy that will be given out. So hoping that that is clear. Yeah, I hope you have also seen about the units, because this 460, we are saying that our Q will be equal to, our Q will, when we cross multiply, will be equal to mass multiplied by the specific heat capacity multiplied by the change in temperature. So we can see what happens to our units. Mass is in kilograms, specific heat capacity is in joules per kilogram per Kelvin, and our change in temperature is in Kelvin. So this kilogram cancels with that Kelvin will cancel with the other one because this is division, joules per kilogram per Kelvin. So we remain with our joules, and that's why our heat is in joules. So that's the quantity of heat that will be given out. So we want to look at another example. Example 2. So that is our question. A block of metal of mass 1.5 kilograms, which is suitably insulated, is heated from 30 degrees Celsius to 50 degrees Celsius in 8 minutes and 20 seconds by an electric heater coil rated 54 watts. Find part 1 of the question, the quantity of heat supplied by the heater. So this question is divided into 3 portions, we'll see. So first we want to calculate the quantity of heat that is supplied by the heater. And since we have the power rating of the heater and we know the time that it takes to supply that heat, then we can calculate the quantity of heat. So we know that quantity of heat will be given by power multiplied by time from the Joule's law. So power times time. So our power, we have been given in its SI unit as 54. Then we multiply by time in seconds. So here we have 8 minutes. We convert it into seconds by multiplying by 60. So our time will be 8 times 60. That's what we have. Then we have and 20 seconds. So here we add plus 20. That way. So we have 54 multiplied by the total there, which is 8 times 60, then plus 20. So we'll end up getting this as 54 multiplied by, this is 8 times 60, which is 480, plus 20, which is 500. So we end up getting our heat energy, or the quantity of heat supplied by the heater, as 54 multiplied by 500, which is 27,000. And this is heat, so it is in joules. So we have 27,000 joules. Is it clear? So we can move on to part B of the question. So we are told to find B. So part B, we are told to calculate the heat capacity of the block. Remember, the block is being heated using a heater. So a block of metal of mass 1.5 is suitably insulated and it is being heated. And here we are assuming that there is no heat loss. So we are told that it is suitably insulated. That is to minimize heat loss to the surrounding. So in this question, we assume that heat loss is negligible. So all the heat that is being supplied by the heater is being used to heat the metal block. So heat capacity of the block, we remember that heat capacity is given by the quantity of heat, in our case supplied, divided by the change in temperature. So our heat capacity, the heat that is being supplied, is 27,000 joules. And the change in temperature, it is being heated from 30 degrees Celsius to 50 degrees Celsius. So the change in temperature will be 50 minus 30, and these are Kelvin. So we are going to have 27,000 joules divided by 20 Kelvin. Divided by 20 Kelvin. So we end up getting our answer for that. That is 27,000. We are dividing by 20, which we get as 1,350. That is the heat capacity, and it is in joules per Kelvin. Remember, we have seen that this change is in Kelvin, which is the SI unit, because even if we get it in degrees Celsius, it's still 20. If we convert it into Kelvin, you still get the same. So we say that it is 20 Kelvin. So when you divide this, you end up getting 1,350 joules per Kelvin. So finally, part C of the question. So we are told to find part C, find the specific heat capacity of the block. So that is very easy now that we have the heat capacity, and we say that specific heat capacity is heat capacity per unit mass. So we have our specific heat capacity as heat capacity, which is 1350 joules per Kelvin, divided by the mass of the block in its SI unit, which we are given as 1.5 kilograms. So we just come and divide by 1.5 kilograms. So what do you end up getting as the specific heat capacity? You simply divide 1,350 by 1.5. So you end up getting that the specific heat capacity of the block is 900 joules per kilogram per Kelvin. So that's how we approach that question and many others that you can be given on specific heat capacity. So I'd like to leave you an exercise, 2 questions to attempt. So that's the exercise. Number 1, find the final temperature of water if a heater source rated 50 watts heats 100 grams water from 25 degrees Celsius in 5 minutes. We've been given the specific heat capacity of water as 4,200 joules per kilogram per Kelvin. Number 2, calculate the heat evolved when 100 grams of copper are cooled from 90 degrees Celsius to 10 degrees Celsius. And the specific heat capacity of copper is 390 joules per kilogram per Kelvin. So calculate and ensure that in your calculations you remember to express all the units in the SI units. So during our next lesson, we'll continue with the specific heat capacity, but in this case we'll advance more and be in a position to get more calculations or numerical problems on the specific heat capacity. So you can join me in our next lesson. Thank you.